Swayam Prabha. Digital India. Educated India.
Now we are going to discuss the problem related to inner product spaces. Let us start with the example. Let x equal to 3, minus 1, 4 and y equal to 2, 5, 2 be the two vectors. What is the value of the standard inner product? Simply inner product x comma y means you take 3 of first x and 2 from the first axis of y and multiply them 3 into 2. Next one is minus 1 into 5 and third one is 4 into 2. So, it becomes 6, it becomes minus 5, it becomes 8, then add them, we have what? The value is 6 plus becomes what? 1, these 2 and then plus 8 equal to 9 will come. So, this is the way we can use the inner product of two vectors. Now, based on this definition, let us go with higher problems. Let us consider a vector space C. C is a complex in n tuple and is similar to the space R power n, but the component of the vectors and scalars are allowed to the complex numbers, and we have to discuss the standard inner product C power n defined by the equation inner product x comma y equal to x1 into y1 bar plus x2 into y2 bar and so on xn into yn bar if it is a complex. Previously we discussed the problem is real, and if you have a complex and the coordinate of y is, you have to take the conjugate and do that. So, you can get it what? The product of two numbers, that is the meaning of inner product x and y. Now, the inner product can be written in the different ways like xy equal to y power h of x, and we can generally denote at summation j equal to 1 to n xj and yj bar. So, for the column vector y equal to y1, y2 and so on yn, so the complex conjugate transpose is the row vector yh is equal to y1 bar, y2 bar and so on yn bar. So, the superscript h calls for the conjugate transpose of the matrix in the honor of Charles Hermite, and the footnote is given in the chapter, and the Hermitian A power h becomes the simple transpose of A transpose for the matrix in the real case. So, this is the general definition of the inner product x comma y. Next example, in the real number R, we can select a vector w equal to w1, w2 and so on wn, whose components are all positive, and we have to define another inner product x comma y is w1 x1 y1, w2 x2 y2 and so on wn xn y1 if w is a vector and if all are positive, and we define the inner product in terms of x comma y. So, the solution is the positive numbers wj are called the weight in this context. So, we do to specify the positive components wi. So, it is ensured that the positivity of x comma x as demanded in the first postulate, and in some application it is helpful to use this more versatile type of the inner product. Next example, what is the simple inner product in the vector space of C of a comma b? Now, here C of a comma b consists of all the continuous real valued function defined in the closed interval a comma b, and inner product often used in the space is f comma g is equal to integral symbol a to b f of t g of t dt. So, this is the what corresponding definition of the inner product f comma g. Even you can define the inner product in terms of the other way. So, If it is in the form of the integral, corresponding the definition is integral f comma g equal to integral a to b f of t g of t dt. Next, norm in the inner product can be represented as norm x equal to root of x comma x. So, in the organ plane you take x axis and y axis. So, x1 axis in the x axis and x2 in the y axis, and then you have a vector, the point x1 x2 determined with the help of the norm with related to this picture is a root of x comma x is a distance from this point to that point. So, that is the meaning of norm. Norm is a length from 0 to x1 comma x2, that is a norm of x. Next example illustrates some of the algebraic operation using the vectors x, y and z or the 3 vectors. Now, let us start with solving the problem of inner product x comma y mean. So, that is x you know. So, x equal to 3, 2 minus 4 and y equal to 2 minus 5, 6, and then inner product x comma y is 3 into 2 plus 2 into minus 5 plus minus 4 into what 6. So, that the resultant will be minus 28. Suppose if you want 3x comma y mean, you have to multiply 3 into what 3 comma 2 comma minus 4 comma y is 2 minus 5 comma 6. Then what I have to do, 3 into 3 is 9, 3 into 2 is 6, and then 4 into 3 is minus 12 comma 2 minus 5 comma 6. Then 9 into 2 plus 6 into minus 5 plus minus 12 into 6, and then the resultant will be what minus 84 will come. So, this way we can calculate what the vectors of x comma y, 3x comma y. Similarly, we can calculate what x plus y comma z. X you know, right, what is x? X equal to 3, 2 minus 4 and y equal to what 2 minus 5, 6, and then x plus y equal to simply add 3 plus 2 5 and 2 minus 5 is minus 3 and minus 4 plus 6, minus 4 plus 6 is plus 2. So, this is x plus y. Now, x plus y comma z is nothing but what that is 5 minus 3 2 of what y z is what minus 2 1 4 and then 5 into minus 2 plus minus 3 into 1 and then 2 into 4. So, we have the net result is minus 5. So, this way we can calculate what between the inner product of x plus y comma z. Next, norm x equal to x you know, another x you know, and simply square them 3 square plus 2 square minus 4 square, so that this will become. So, norm x is nothing but what root of what 3 square plus 2 square plus minus 4 the whole square equal to root of 9 plus 4 plus 16 equal to root 29 will come. Similarly, x by norm x is simply divide them. So, this way we can do that what the area of what finding the norm. Next, we will have an example, continue with some examples of the vectors with the complex entries such that u equal to 2 plus I comma 4 minus 3I and v equal to 5 minus 2I comma 2 plus 3I, and we have to calculate inner product u comma v. So, inner product u comma v is nothing but what 2 plus I comma 4 minus 3I into what v V is 5 minus 2i comma 2 plus 3i. So, it becomes what? So, taking this simply multiply them. So, 2 plus I into 5 minus 2i plus 4 minus 3i into 2 plus 3i. So, this is things we have to calculate. Therefore, what happened? 2 into 5, 2 into 5 is 10 minus 4i and then plus 5i and then minus 2i square plus similarly you have 4 into 2 8 and then 4 into 3 is 12i and then minus 6i and then minus plus minus 9i square, that is plus 9. So, the resultant will be what? 7 plus 9i will come. So, this is a way we can calculate what? U comma V. Similarly, V comma U is, and then reciprocate it V and U, because conjugate you have to take it, so that we will get what? 7 minus 9i. And U you take it, U you know, and then another U you know, simply you have to multiply VV equal to 42 and U plus V, U you know, add V, so that U plus V will come. So, U plus V and U plus V equal to 86. So, this way we can calculate what? The values of UV, VU, UU, VV and U plus V and V plus U. Next example, suppose the inner product being used is weighted like this: x comma y base W equal to 3x1 y1 plus 2x2 y2, where W equal to 3 comma 2. So, let x equal to 5 comma 2, y equal to minus 1 comma 4, then xy is nothing but what? X you know, y you know, and then W, and W is 3. So, what you have to do is W, take it in a way like that. First you have to do xy. So, 5 into minus 1 and then 2 into 4 and then W is 3 corresponding to, so that the value of x comma y base to W equal to 1 will come. So, this is also we can do with the help of the inner product x comma y W. So, the expression is given of the definition of inner product x comma y base W equal to 3x1 y1 plus 2x2 y2. So, substitute it and then based on the W you can generate with the help of inner product x comma y. So, based on the picturization you take a x, find the norm x and y, norm y find out and then add them corresponding. So, x plus y will come. So, this is the based on the triangle inequality of the two functions. So, this is the inference we have to learn from this example. Next definition: two vectors x and y are mutually orthogonal if inner product x comma y equal to 0. So, keep it in mind the definition, and then they are mutually orthogonal mean take inner product, find the value, 0 comes, ultimately we can say it is a mutually orthogonal. Find orthogonal basis and orthonormal basis for RQ, starting with u equal to 3, 5, 1 and v equal to 2, minus 2, 4. Now, we seek the non-zero vectors x equal to x1, x2, x3 and u comma x equal to 0, v comma x equal to 0. This leads, so 3, 5, 1 of x. X mean x1, x2, x3 equal to 0 mean 3 into x1 plus 5 into x2 plus 1 into x3 equal to 0. So, this is the representation of this. Similarly, we have another vector v. V is what? This can be written as the inner product 2, minus 2, 4 corresponding to x1, x2, x3 of this one equal to 0 mean 2x1 minus 2x2 plus 4x3 equal to 0. So, this is the representation of this equation. Now, we have to convert into matrix. So, what is the coefficient of x1? 3, coefficient of x2 5, coefficient of x3 is 3, and for second equation 2 minus 2 4. So, this is the things we have learned, and then we have a what row reduce, that is make this one equal to 1 and make this one equal to 0. Therefore, R2 such that R2 minus that is this R3 divided by 3, the 1 by 3 into that is 2 by 3 into R1, you do that, so that the value will comes like this. So, make the entry of 1 0 0 1, 11 by 2 minus 5 by 8 will come. So, the solution is x1 equal to minus 11 by 8 into x3, x2 equal to 5 by 8 x3. So, the solution is x1 equal to minus 11 by 8 into x3 and x2 equal to 5 by 8 x3. So, x3 is a free variable. So, that you choose the value of x3, suppose x3 equal to 8 and then corresponding x2 equal to 5, x1 equal to minus 11 will be generated. Therefore, the values of x equal to minus 11, 5, 8. So, the column of the matrix from form and orthogonal basis UVX as what 3, 5, 1 and 2 minus 2, 4 and minus 11, 5, 8 from this expression. So, now you have to start with what transpose A is 3 cross 3, then we have to transpose A transpose is there is a rows to column, columns to the row, so that the matrix will come. A is a given matrix, right. So, this is A transpose, this is A and multiply them, we have beautifully the diagonal element only will come and above diagonal below diagonal will be 0. So, this way also we can get it the diagonal elements of the given matrix. Now, based on this you find the norm of U square. You know 3, 5, 1, take norm of U is equal to what? That is root of 3 square plus 5 square plus 1 square, root of 9 plus 25 plus 1. So, root of 35 like that will come. So, root of 35, for norm U equal to root of 35. Similarly, norm V square equal to 24, norm X square equal to 10 will come with the help of the previous ideas. So, the column of the next matrix form an orthonormal basis like, so 3 by root 35, 5 by root 35, 1 by root 35. For second 2 by root 24, minus 2 by root 24, 4 by root 24, and third one minus 11 by root 210, 5 by root 210, 8 by root of 210. Therefore, we have a matrix and we have to find out what this is called as matrix A into D inverse diagonal matrix. So, verify that and superbly will come A transpose A equal to diagonal and of diagonal multiply you can get it, and similarly D minus of A transpose A root D of A D power minus of equal to I will come, and B into B transpose or B transpose B equal to identity will come. So, this is the inference we calculated with the help of the matrix and from the vector. Next, orthogonal projection, right. So, this is the orthogonal projection. If you take a vector P on the y axis and a x minus P on this, so this resultant is called as x minus P. For example, you take a 3 tuple, the standard inner product. What is the orthogonal projection of the vector x equal to 1, 2, 3 onto the vector y equal to 3, 2, 1? So, the answer is we need to compute the projection as follows. So, rule is P equal to inner product x comma y by inner product y comma y into y. So, inner product x comma x is nothing but inner product of 1, 2, 3 of 3, 2, 1, and then you have to write 1 into 3 plus 2 into 2 plus 3 into 1. So, which is equal to 3 plus 4 plus 3, which is equal to 10. Therefore, inner product y comma y is equal to root of 3 square plus 2 square plus 1 square root of 9 plus 4 plus 1, which is equal to root 14. Therefore, this is called as root of inner product x comma y. Therefore, inner product x comma y is 10 by root 14 into y. So, y is nothing but 3, 2, 1. So, 10 by 14 is 5 by 7, right, 5 by 7. So, 5 by 7 of the vector 3, 2, 1 will be generated corresponding p value. So, one can also verify x minus p is orthogonal to y. So, we obtain x minus p comma y is x minus p the transpose y. So, x you know the vector 1, 2, 3 and minus p is 5 by 7, 3, 2, substitute it and transport it, and corresponding y value 3, 2, 1 of the inner product, do that, and we have what the vector becomes 0. So, it means they are orthogonal to one another. So, this is called as orthogonal projection, and this is the corresponding values. Now, angle between the vectors. Angle between the vectors means suppose A and B are the two vectors, and then how to find the angle? Then law of cosines apply it, cos theta equal to A dot B mod A mod B, A dot B equal to mod A mod B cos theta equal to this will come, or cos theta equal to using the inner product x comma y by norm x into norm y, or in terms of the norm you take a x and y, the length norm x and norm y, and the difference of this one is norm of x minus y. So, this way we can apply with the angle between the two vectors. What is the angle between the two vectors? X equal to 1, 3, 7 and y equal to 3, 2, 4. So, the solution to the formula is cos theta requires these ingredients x comma y equal to 31. Norm of x is nothing but inner product x comma x, which is equal to root of 1 square plus 3 square plus 7 square root of 1 plus 9 plus 49 equal to root of 59 will come. So, that is written here. Similarly, norm y equal to root of minus 3 square plus 2 square plus 4 square, which is equal to root of 29, that is what written here. So, the rule for finding the angle is cos theta equal to inner product x comma y by norm x into norm y. Inner product x comma y represent, so 1 into minus 3 plus 3 into 2 plus 7 into 4. So, we have inner product is value is 31. So, 31 by what norm x into norm y is root 59 into root 29 is root of 1711, and simplify it is approximately 0.74944, and theta theta is what? Theta is cos inverse of what? This value, and then we have theta having 0.72358 radians or 41.458 degree corresponding conversion. So, this way we can find the angle between the two vectors. Next, orthogonal complements. Orthogonal complements mean of a set S in an inner product space is the set X such that X is perpendicular to S for all S in S, or X is perpendicular to S if they are orthogonal complement of S is denoted by S perpendicular. So, that is the meaning of two vectors are complement to one another. So, let us go with one example. Is the vector x equal to 3, 7, 1 is orthogonal complement of the pair of the vector u comma v, where u equal to 5 minus 2 minus 1 and v equal to 2 minus 3 15. So, orthogonal complement of u v, the vector x must be orthogonal to u and v. Now, the orthogonality is confirmed the follows: x comma u is an inner product, x you know, u you know, then corresponding entry you have to multiply. So, that 3 into 5, 7 into minus 2, 1 into minus 1, which is equal to 15 minus 14 minus 1 equal to 0 will come. They are orthogonal complement to one another. Similarly, x and v you take it, inner product find out, you know x 3, 7, 1, you know v, this is the value. So, 3 into 2, 7 into minus 3, 1 into 15. So, that after simplification 6 minus 21 plus 15 equal to 0 comes. They are orthogonal complement to one another. Next example, let U be the subspace of R cube and whose basis consists of the two vectors U given and V given as in the example 9 is the vector x is the orthogonal complement of U. So, the solution is already we checked x is orthogonal to U and V. Now, we conclude that x is orthogonal to span of U and V, which is U. That is the answer to the question. Next example, let x equal to 3, 7, 1. So, what is the dimension of orthogonal complement of the single vector? Now, we see the example 10 shows that U and V are in this orthogonal complement. Neither U nor V is a multiple of the other. Hence, they span the two-dimensional subspace of R cube. So, therefore, it is a complement of a single vector of x. Another example, find the basis for the null space of the matrix 2 rows and 3 columns and verify that the null space of the orthogonal complement of the row space. Here, the simple description of the null space of this matrix means we use the row reduction to solve the homogeneous equation Ax equal to 0. Therefore, we have 5 minus 2 minus 1, 2 minus 3, 15. Now, we have a row reduced, that is first you convert, keep second row as it is. The first row you have to simplify and convert, this is 1, that is R1 such that R1 minus 2 times or 3 times of R2, right. So, that it will be reduced to 1, 4 minus 3 will come and go ahead like that. We have 1, 4 minus 3 was 0 minus 1, 11, 77 and below this also is 0 and 1 come. So, that identity matrix will be described. Now, we have identity matrix and corresponding value, we can easily find the solution Ax equal to 0. Now, we obtain from the previous x1, this is x1 and corresponding x3 equal to minus 3x3. So, that is x1 minus 3x3 equal to 0. From the last row we convert x2 minus 7x3 equal to 0. Therefore, we have the general solution is what? x1 x2 equal to x3 of 371. Therefore, the null space is the one dimensional which is spanned by the vector 371. Therefore, our example shows that orthogonal complement of the row space generated by the same vector. So, next example, in the space the continuous function 0 comma pi consists of all continuous function on the interval 0 comma pi. We consider the sequence of the function defined by wkt equal to cos of kt, where k is you take the value 0, cos 0 is 1, and when k equal to 1 cos t will come, when k equal to 2 cos 2t will come, and check it out, w1, w2, w3 and so on start from 0, w0 equal to 1. So, 1 cos t, cos 2t, cos 3t and so on it will come, and we define a function w1 in the sequence, and is this an orthogonal sequence or not, that you have to check it out. The technique is you compute the inner product wk comma wj, say you start from k equal to 0 and you do not take k and j are the same value. Suppose you start with w0 and you take w1 like that and go ahead with like that, and k and j are not equal, and refer the example and using the standard trigonometry function formula. So, we obtain wk into wj is nothing but integral 0 to pi cos kt and cos jt dt. So, this is what we written in the example 4. So, example 4 you check it out. So, this is the representation of integral symbol, inner product f comma g is equal to integral a to b f of t gt dt. So, using the definition of inner product wk wj, we have integral 0 to pi cos kt into cos jt dt. Therefore, off into integral 0 to pi cos of cos a cos b. So, you have cos of a plus b plus cos of a minus b equal to what? Cos a cos b minus sin a sin b, then plus cos a cos b plus sin a sin b, we have the formula, and then we implies 2 times of cos a cos b will come, but we need only cos a cos b. Therefore, this implies cos a cos b equal to half times of cos of a plus b plus cos of a minus b, and using this formula cos of a, this is a and this is b, cos of a plus b is cos of kt plus jt. Therefore, cos of k plus j into t and cos of k minus j into t will come, and then split it into integral. Integral of cos of k plus j t is cos of sin k plus j t by k plus j. Integral cos of k minus j dt equal to sin of k minus j into t by k minus j, and apply the limit 0 to pi, and sin pi is 0 and sin 0 is 0. Therefore, in both case the value becomes 0 and net value is 0. Therefore, as per the definition, they are orthogonal sequence. So, here we use this trigonometric concept of sin of a plus b equal to sin a cos b plus cos a sin b. If sin of a minus b equal to sin a cos b minus cos a sin b. Similarly, cos x plus cos y equal to 2 times of cos of half into x plus y into cos of half into x minus y technique, use it, so that we can write the sequence pattern of the cosine functions, and orthogonally they are project, or orthogonally they can be sequentially project. Next, orthonormal basis. A real matrix U is orthogonal if U transpose and U transpose U equal to I, right. So, the matrix entry are real, then we have to use this. If it is complex matrix, U is unitary if U power H equal to U power H into U equal to I. Now, we have an example. Here is the matrix whose columns form an orthogonal set. Let A equal to 4 1 1 1 2 minus 2 minus 2 3 1. Now, by normalizing each column and produce the orthogonal matrix, find a further interesting relation and the inverse of U. Now, each column must be divided by its norm, that is, you take 4, this 4 can be written as 4 by root of 4 square plus 1 square plus minus 2 square, that is 4 by root of 16 plus 1 plus 4, which is equal to 4 by root 21. This is what they written, 4 by root 21. Similarly, 1 by root 21 minus 2 by root 21, and similar by second column you take it, 1 by root 14, 2 by root 14, 3 by root 14 will come. Third, the same way, 1 by root 6 minus 2 by root 6, 1 by root 6 will come. Therefore, we have the column of U form an orthonormal basis and the row do the same. Therefore, the matrix U is obtained by multiplying A on the right of the diagonal matrix, and we have a diagonal entries only will come. So, that is the inference. Once you get it, U and A d power minus half means the diagonal multiply. So, that U and U transpose multiply, I will come, and U you know supply here and transpose, and then you take it and simplify, it becomes A transpose d power minus half transpose into A transpose and A into d power minus half, and I equal to U transpose we have like this, and simplify we have A transpose will come. So, this is the inference you have to learn with the help of the diagonal matrices. Now, we have applications. So, work and forces. We can describe the work and forces in terms of the notation and concept discussed in this section. Let the vector F be the force exerted on an object. Let the vector D be the displacement caused by the force, and let theta be the angle between F and D. For example, suppose we are pulling a heavy load on a dolly with the constant force so that it moves horizontally along the ground. So, the work done in moving the dolly through the distance d is given by distance moved multiplied by the magnitude of the component of the force in the direction of the motion. So, this demonstrated in the figure 7.5, the component F in the direction d is norm F into cos theta. Therefore, according to the definition of the work can be written as norm F into dot norm d into cos theta, rather we can write inner product F comma d. So, this is the mathematical modeling of the force and displacement if you have the what ideas like this. So, having the force and the distance between the angle, we have a what work done by the force. Now, we have a application, the collision. So, law of collision can be applied to determine the final location of the ball after glancing the collision with the wall, as shown in the previous figure. Let U equal to U1 and U2 be the initial position, and V equal to V1, V2 be the final position. Then they can be written in the form of the pair. Then U minus V be the change in the position as a result of the collision, according to law of cosines, we can write norm of u minus v square is equal to norm u plus norm v square minus 2 norm u into norm v cos phi is the expansion. From this expression we obtain inner product u comma v equal to norm u dot norm v cos phi. So, this is the way we can apply using the inner product of this application. So, which gives the connection between the inner product of the vectors u and v and the angle phi is between what? Suppose you are throwing a ball, start from this and then reflect here, so that norm u norm v is reflected like this. Then the distance between is norm of u minus v is calculated like this, and this is called it as glancing ball of corresponding real time application. That is all.